Okay, the what goes up must come down graphs. The ball is launched up with a velocity of 29.4, eventually falls back down. So this number I picked because hopefully that makes some numbers nice. It's a multiple of the 9.8 value. It's exactly 3 times 9.8. So hopefully that'll help make some of the numbers nice for us. Okay, so part A, I asked you to draw a velocity time graph first. And that's actually easier, in my opinion, compared to the position time graph. So we'll start with the velocity time graph. Like, how might we approach this? So I know what the starting velocity is, so that's good. It starts at a velocity of 29.4. And then 1 second later, it's going to be slower by 9.8. And then another second after that, it's going to be slower by another 9.8. And then another second after that, it'll be slower by another 9.8. It's going to be a constant acceleration. That's important in terms of the shape of the graph you're going to draw. A constant acceleration means that you're going to draw a straight line for your graph. A straight line with a negative slope, probably, because if we choose up as positive and down as negative, well, the acceleration, which is down, well, that would be negative then. Okay. When is it at rest? That's going to be a key point of my graph. Like, when does it reach the top? Maybe that's a better way to say it. Yeah, I want to calculate this out first before I go ahead and start graphing, because this is going to be a key spot of my graph. Okay, so I'll do the algebra here, make a list. So my V1 is 29.4 meters per second up with an acceleration of negative 9.8 meters per second squared up. And when it reaches the very top, it comes to a momentary stop. So V2 will be 0 at the very top. And I want to know when this happens, so delta T is a question mark. To go back to all my kinematics equations and find the suitable one, so it's going to end up being this equation here. I do have them memorized, yes. And I solve for the time. When I solve for the time, this is like a common situation, I guess I would say, where basically the acceleration and time in this formula are just going to trade places. When you do the algebra steps, that's just what ends up happening. And I've done it so many times that I can just recognize that. All right, I can fill in the values. So 0 minus 29.4 divided by negative 9.8. And as I said, I chose that number because this, when you divide it, should equal exactly 3. So 3.0 seconds. Okay, so I'm going to go ahead and attempt this graph now. So it's a velocity time graph. So label time, seconds, and then velocity, meters per second. I'll choose up as my positive direction. And I'm going to plot my key points. My key points are 3 seconds. Okay, I just calculated 3 seconds is when it comes to a rest. So that'll have a velocity of 0. And then my starting velocity is another key point. My starting velocity is 29.4. And what goes up must come down. This is a symmetrical situation here. It's going to spend 3 seconds going up and then 3 seconds coming back down to hit the ground. So it's going to end up at 6 seconds. And the velocity is just going to be negative 29.4. A symmetrical situation. It's not always symmetrical. This one is symmetrical because it started on the ground and ended on the ground. Some more complex situations maybe, well, what if you start at the top of the building and then you end at the bottom of the building? Well, then that's not as symmetrical. Okay, so I'll just draw a straight line, really. I'm going to use the line function tool. And that would be my velocity time graph for this question. Okay, B, draw a matching position time graph. Oh boy. All right. So, how shall I explain this? Okay. Time, position, meters up. So the ball is going to start on the ground, so the starting position is 0. The ball is going to end on the ground, so the ending position, which is 6 seconds later, occurs 6 seconds later, is also on the ground. Okay, that 6 seconds just matches my velocity time graph. And in the middle, at 3 seconds, that is when it reaches its highest point, somewhere up here. And this, I'm just going to connect these 3 points in the shape of a parabola. Oof, that second part does not look so good. We're going to live with it. Okay, how do we know it's a parabola? Well, first of all, that's something you'll learn in a bit more detail when you get the calculus treatment of physics. But since we're not there yet, it's coming from, you can think of it from this formula. So algebraically, this is one of our formulas, and you see that the position or the displacement is a function of time, but there's a squared term there. So that makes it a quadratic type of equation. And quadratics, you should know, hopefully from grade 10 math and grade 11 math, they graph out parabolas when you graph them. So it is a parabola there. But if you did not know that, you should still know that it's curved. You should still be able to figure that it's curved because it's supposed to be slowing down for the first half. That means it needs to get less and less steep. So that's represented by a curve. It flattens out at the very top. And then in the second half, it's it starts speeding up again and moving downwards. So it's got to get more and more steep for the second half. So at least the curved shape you should know. Now, one more detail I would like to add to this graph is the number for the top here. It's going the extra mile is to figure out the number that goes there. So what is the maximum height that this ball reaches? Just to practice, right? To practice these maximum height type questions. So for a maximum height question, I'm basically going to use the same sets of, the same three givens there as part A. And then instead of finding the time, I'm going to find the displacement. How much did it displace for the first half? And that'll give me the maximum height. So that's going to be found with one of our big 5 equations. And we're going to solve for displacement. So first of all, 0 for V2. And then rearrange things. So negative V1 squared over 2A will end up being the displacement. And putting in the values. Okay, let's go to the calculator, even though I've had issues with it. 29.4 squared divided by 19.6 gives me 44.1. Okay, so that allows me to fill in that number on the graph just to give myself a little bit more detail and full marks. All right, so that is the what goes up must come down graph.